Welcome to This Explainer. I am absolutely thrilled you're here with us today, because today we're doing something incredibly exciting. We are opening up the Problem Solvers Toolkit. We're going to dive right into solving some genuinely complex puzzles using mathematical tools. Now, try not to think of this as a typical math lesson. Instead, think of it as an exploration into the very language of logic that literally shapes the entire world around us.
So how do we actually mathematically predict the unknown? A lot of people think math is just rote memorization, just a bunch of formulas you cram into your head for an exam, right? But it's really not. It's this incredibly powerful, elegant system that we use every single day to organize the sheer chaos of reality. It is exactly how we find certainty in a world that is just full of random variables.
Here's our roadmap for today. First, we'll look at the language of chance. Then, we'll move into decoding the data. And finally, we'll wrap up with navigating space.
Okay, let's dive right into this. Section 1. The language of chance and how we measure uncertainty.
Before we can predict anything at all, we really need to know what we're working with. And that brings us to an absolutely crucial definition: sample space. This is literally the foundation of probability. It represents the total number of all possible elements or outcomes in any given experiment. For instance, think about flipping a fair coin. If you toss that coin 3 times, your sample space contains exactly 8 unique elements. Every single possible combination of heads and tails is accounted for right there in that space.
Right, let's lock in one more secondary foundational rule before we start calculating the fun stuff: mutually exclusive events. These are events that absolutely cannot occur at the same time during an experiment. You can't roll a die and get a 2 and a 5 simultaneously on the exact same face. Taking a brief moment to firmly establish these boundaries gives our brains the structure we need to solve much more complex problems.
Let's put this into practice with a totally relatable everyday choice: Alemu's morning routine. He's standing right in front of his closet, facing a wardrobe dilemma. He's got 4 coats, 5 shirts, and 2 trousers. So how many different ways can Alemu actually dress? Well, this is where combinations come to the rescue. You simply multiply the independent choices together. 4 times 5 times 2 gives us 40 total unique ways for him to dress. What seems like a chaotic closet is actually a perfectly ordered mathematical multiplication.
But wait, what happens when the exact order actually matters? That's when we bring in permutations. Say you take the letters in the word ananas. Because of those repeating A's and N's, there are exactly 60 distinct permutations, or ways to arrange those letters. Or imagine hosting a dinner party. If you're trying to seat 6 people around a circular table, there are 120 different permutations for how they can be seated. The complexity definitely ramps up, but our toolkit handles it effortlessly.
So, by understanding sample space and the rules of combination, we can confidently declare exact probabilities. 5 over 36. That is exact mathematical probability of getting a result sum greater than 9 when rolling 2 dice. It's not a guess, it's not a hunch, it's a solid, derived fact pulled straight from the chaos of rolling the dice.
Moving on to Section 2, decoding the data and making sense of numbers. To really decode data, we first have to sort it into 2 main buckets. On one side, we've got quantitative data. These are your hard numbers, like counting the actual number of math teachers in a school. On the flip side, we have qualitative data, which is descriptive information. Picture things in your own life, like a person's social status, the name of the street they live on, or the brand of car they drive. These describe qualities, not quantities.
And we can refine our toolkit even further by breaking down those hard numbers. Continuous data involves measurable amounts that can be broken down into infinitesimally smaller fractions. Think about the exact distance you travel between classes. Now put that side by side with discrete data, which are distinct, countable values. You can't be ranked 2.5 in your class, right? A student's rank or grade level is a solid, discrete integer.
Now we can take all that discrete data and visualize it beautifully in a frequency distribution table. The X row shows our values, and the F row shows the frequency, literally how often those values occur. We can multiply each value by its frequency, add them all up, and divide by the total number of items to find the mean. And for this specific data set, the mean elegantly works out to exactly 5.
Let's keep this momentum going. When data sets get absolutely massive, we group them into class intervals. But to calculate statistics on group data, we still need a single representative number. Enter the class mark. It's the exact average of a frequency distribution's lower and upper class limits. It beautifully finds the dead center of your group data, so you can just keep calculating without missing a single beat.
And once our data is nicely organized, we can slice it up to understand its distribution.
We use deciles and quartiles to chop vast datasets into incredibly useful, digestible percentages. For example, looking back at our previous dataset, the fourth decile, or D4, equals 4. Or consider this. If the first quartile, Q1, of a dataset is equal to 24, that immediately tells you that exactly 25% of the entire data falls below the number 24. It's kind of like having X-ray vision for numbers.
All right, on to Section 3, Navigating Space, Transformations and Vectors.
Okay, I want you to vividly imagine a massive coordinate plane in your mind. A translation is simply a mathematical rule that physically shifts a point across that space. If translation t takes the origin, 0, 0, and slides it over to the coordinates 4, -3, well, it applies that exact same movement to every single point. So point A, originally sitting at 8, 5, gets seamlessly mapped to its new image at 12, 2. It's pure spatial movement completely defined by numbers. Let's see how this builds into geometry. Finding the tangent line of a circle might sound intimidating, but honestly, it's just a step-by-step process. Step 1, we locate the center of the circle from its equation. Here, it's at C23, and we note the radius squared is 29. Step 2, we identify our target point touching the edge at 4, 8. Step 3, we calculate the slope between those points and find the perpendicular line to lock in our tangent equation. See, it's a perfectly logical sequence.
Now, what's really interesting about this concept is how we inject direction and magnitude into our space using vectors. Consider vector u, which is 8i minus 4j. It is completely parallel to the vector 2i minus j simply because they share the exact same proportion and direction. However, look at 16i plus 8j. Because of that positive 8j, its direction is completely misaligned. One simple sign change alters its trajectory entirely, no way around it.
Of course, knowing a vector's direction is only half the battle, right? Knowing its length is the other half. The vector norm is the total length or magnitude of a vector. This becomes heavily utilized when we push into complex 3D equations, like finding the exact length of vector v equals I plus the square root of 5j plus 4k. The vector norm gives us a firm, indisputable measurement of length to a direction floating out there in three-dimensional space.
And here we go, the climax of our spatial segment. How in the world do you find the area of a triangle that is literally suspended in three-dimensional space? Well, we map the vertices, A, B, and C as seen in Step 1. In Step 2, we take the vectors spanning between them and calculate their cross product. Finally, in Step 3, we use the norm of that cross product to perfectly extract the area of that 3D triangle. We've taken pure, abstract data and turned it into a measurable physical area.
Probability, statistics, and geometry intertwine to form the ultimate language of logic. Throughout this explainer, we've seen exactly how true that statement is. From Illumiu's closet combinations, to the frequency distributions of discrete data, right up to the cross products of vectors in 3D space. These aren't just isolated exam questions, they are a beautifully interconnected language that allows us to make sense of the world.
And that brings us to the end, and to a question I want to leave you with. How will you use this toolkit to decode the unknown in a choice you make today? Mathematics is not just stuck on a chalkboard. It is in the choices you make, the data you encounter, and the physical space you navigate every single day. Take these tools, step out into the world, and start solving. Thank you so much for learning with me today.